Picture a lighthouse on a cliff. Its beam sweeps around at a steady speed. Can we predict exactly where that spot of light will land on the shore at any moment? That sweeping beam traces out a perfect circle. Hidden inside that simple shape is a secret code linking height, distance, and angle. Let's crack it. We just saw a lighthouse beam sweeping the shore. Now, let's build a special measuring tool, a circle with a radius of exactly 1. We call it the unit circle, meaning 1. Any point on this circle has coordinates x, y. For a given angle, the x-coordinate is the cosine, and the y-coordinate is the sine. The circle turns angles into numbers. Because the radius is 1, the math stays clean. The hypotenuse of any triangle we draw inside is always 1. This makes the sine and cosine value simply the lengths of the triangle's legs. We just built the measuring wheel. Now see why it matters. Spin the radius and you instantly create every possible right triangle. The radius stays 1, so cosine and sine give you the exact leg lengths for any angle. A triangle is just a snapshot. But as the angle grows, the height traces a perfect wave, the same shape that describes sound, light, and tides. One circle unifies static shapes and flowing motion. We just built our measuring wheel. But why does a circle replace a whole toolbox? Because every right triangle is just a snapshot of a spinning radius, and a radius of 1 lets us read measurements directly. Watch the point move. At 0 degrees, the triangle is flat, no height. As the angle opens, the opposite leg grows. At exactly 45 degrees, the two legs are equal, so sine and cosine have the same value. That's the promise. Any right triangle you'll ever meet is just this point frozen at some angle. The unit circle doesn't just draw one triangle, it draws them all, and hands you their proportions directly. We just built our measuring wheel. Now, an angle isn't just a corner, it's how much we rotate a ray from the starting line, the positive x-axis, sweeping counterclockwise. But the ray can keep spinning. One full loop is 360 degrees. Keep sweeping and you get 400 degrees, same spot, but a longer journey. The angle measures the total rotation. By always starting from the rightward ray, we all speak the same language. Sweeping counterclockwise gives a positive angle, sweeping the other way gives a negative one, like rewinding the spin. We just measured angles in degrees, but 360 is just a number humans picked. The circle itself has a more natural language, one that comes directly from its own shape. Take the radius, the spoke of our wheel, and wrap it along the circle's edge. The angle that sweeps out that exact arc is called 1 radian. It's the angle where the curved path equals the straight spoke. The whole circumference is 2 pi times the radius, about 6.28 spokes laid end to end. So a full turn sweeps out 2 pi radians. That's the circle's native full circle number, matching 360 degrees. We just learned radians measure distance along the edge. Now let's build our measuring tool, a circle with radius exactly 1, centered where the axes cross. From the center, a ray stretches to the circle's edge. As we rotate it counterclockwise from the positive x-axis, its tip traces the circle. That tip is our point, x, y. Watch the coordinates change. At 0 radians, the point sits at 1, 0. At pi 2 radians, a quarter turn, it's at 0, 1. The angle completely controls x and y. We just built a circle with radius 1. Now, pick any angle, the ray hits the circle at exactly 1 point. that point's x and y are the cosine and sine. Imagine a light shining from far away. The point casts a shadow on the x-axis, that's the cosine. Its shadow on the y-axis is the sine. As the point glides, the shadows stretch and shrink. Watch the point travel. At the top, cosine vanishes to 0 while sine peaks at 1. Halfway around, cosine hits -1. The values flow between -1 and 1, never breaking. We just located our point using cosine and sine. Now, because that point lies exactly on the unit circle, its coordinates must satisfy the circle's equation x squared plus y squared equals 1. Substitute cosine and sine, and the most famous identity in trigonometry falls right out. Look at the right triangle formed by the point, the origin, and the projection on the x-axis. The hypotenuse, the side stretching under the right angle, is the circle's radius, which is 1. The legs are exactly cosine and sine. Apply the Pythagorean theorem, and you get the same beautiful result. This isn't just true for a few angles, it holds for every single one. At 45 degrees, cosine and sine are equal, both about 0.707. Square them, add them up, and you get exactly 1. This unchanging relationship is why we call it the Pythagorean identity. We just saw that sine and cosine are the y and x of a point on the circle. Now, divide them. This new ratio, called tangent, is simply the slope of the radius line, rise over run. At 45 degrees, the triangle is isosceles, two equal sides. The rise and run are identical, so the slope is exactly 1. That's why tan 45 degrees equals 1. Now watch as the angle approaches 90 degrees. The run, cosine, shrinks towards 0 while the rise, sine, stays near 1. The slope skyrockets, becoming undefined at exactly 90 degrees. We just saw the tangent as the slope of the radius. Now, drop a perpendicular straight down to the x-axis. This carves out a right triangle whose hypotenuse is the radius, exactly length 1. The vertical leg, opposite the angle, is exactly the y-coordinate, which we defined as sine. Since the hypotenuse is 1, the classic ratio opposite over hypotenuse simplifies to just sine itself. Similarly, the horizontal leg adjacent to the angle is cosine. And tangent? It's the slope, rise over run, which is opposite over adjacent, or sine divided by cosine. The circle unites all three ratios. We just used SOHCAHTOA inside a right triangle. But a triangle can't have a 120 degrees angle, the radius can. The point's coordinates don't disappear, they just move into new quadrants. As the point swings past 90 degrees, its x-coordinate, cosine, becomes negative. Sine stays positive until 180 degrees. In the third quadrant both are negative, and in the fourth, sine flips negative while cosine recovers. Tangent is just the slope of the radius. In quadrant 2, a positive sine divided by a negative cosine gives a negative slope. The sine pattern, positive, negative, positive, negative, emerges naturally from the coordinates. We just tracked sine and cosine around all four quadrants. Now, let's unroll that circular path into a straight line, plotting the height, sine, against the growing angle to reveal a hidden wave. As the angle grows from 0 to 2 pi radians, the y-coordinate rises to 1, falls to -1, and comes home to 0. This smooth, repeating S-curve is the graph of sine. This length, 2 pi, is called the period, the angle needed for one complete lap. Because the circle is endless, the wave repeats identically every 2 pi radians, forever. We just saw sine and cosine wave forever. Now, let a radius sweep clockwise, a negative angle. Its reflection across the x-axis shows the x-coordinate stays put, while the y-coordinate flips sine. Now reflect that point across the y-axis. The new angle is supplementary, it pairs with the original to make a straight line. The y-coordinate, sine, is unchanged, the x-coordinate, cosine, becomes its negative. Swing the radius through the origin, adding half a turn, or pi radians. The point lands directly opposite. Both legs of the right triangle flip sine, so cosine and sine both become their negatives. We just used symmetry to bounce around the circle. Now let's find exact coordinates, starting at 45 degrees, exactly halfway up the first quadrant. Dropping a perpendicular creates a right triangle with 2 equal legs, so x equals y. Plug into x squared plus y squared equals 1 to get square root 2, square root 2. For 30 degrees and 60 degrees, we start with an equilateral triangle, all sides equal, all angles 60 degrees. Slicing it down the middle gives a 30-60-90 triangle. The short leg opposite 30 degrees is exactly half the hypotenuse, so when the hypotenuse is 1, that leg is 1/2. At 30 degrees, the short leg is the vertical side, sin 30 degrees equals 1/2. Pythagoras then gives cos 30 degrees a square root 3/2. At 60 degrees, the triangle flips, sine becomes square root 3/2 and cosine becomes 1/2. These landmarks anchor the entire first quadrant. We just found landmarks on the circle. Now, imagine shining a light from the side. As our point rotates, its shadow moves up and down, tracing the same sine wave we graphed earlier. A speaker cone works the same way. It pushes forward as the point rises, and pulls back as it falls. One complete rotation creates one vibration cycle, the pitch you hear. This pattern isn't just sound. The electricity in your walls alternates as a sine wave, and even the seasons follow a circular rhythm, all captured by one rotating point. We just saw sound waves unroll from this circle. Now watch the whole story replay. Every idea we built lives right here in one rotating radius. That radius is always 1, so the Pythagorean identity is just the circle equation. And the circle's perfect symmetry gave us all those angle shortcuts for free. And when we let time run, the circle unrolls into the wave we just heard. Every cycle of sound is just one more trip around. We just connected everything, now let's pay off that opening puzzle. Place the lighthouse at the origin, with a beam length of 1. The cliff is the y-axis, and the shore is the vertical line at x equals 1. Say the beam makes a 30 degrees angle with the cliff. Cosine gives the x-coordinate, about 0.866. To reach the shore at x equals 1, we scale the triangle. The spot's height is tangent of 30 degrees, about 0.577. For any angle, the spot's height on the shore is simply the tangent of that angle. As the beam sweeps steadily, the spot's motion traces out the tangent graph, rising, falling, and repeating predictably. We just solved the lighthouse mystery. Now, the single most common slip-up, mixing up cosine and sine. Remember, alphabetically, C comes before S, just like X comes before Y, cosine grabs the X, sine grabs the Y. To recall the special angles, use your left fist. Hold up fingers for 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. The sine is the square root of your fingers, over 2. Cosine runs backward from 4 fingers down to 0. Here's your final challenge. Stand up, point your right arm straight ahead. That's your starting radius. Now slowly sweep it upward. Your arm's height on the wall is the sine, and its shadow on the floor is the cosine.